Dear students, today we are going to discuss about a very important topic in electrochemistry, that is activity and activity coefficient. Activity and activity coefficient. Okay, so let me introduce the term activity first. You see, I'm going to give you one or two examples related to activity. If we take 40% alcohol, 40% alcohol in a beaker. Okay, in a beaker. That means 40% alcohol means 40% alcohol plus water. Okay, 60% water. That means we are dissolving 40% alcohol in 60% water. That you can call it as 40% alcohol. Okay. Suppose you know that there is a pungent smell for the alcohol. Okay, so that smell is actually smell of this alcohol is actually proportional to the vapor pressure of alcohol, you know. Okay, so that means if vapor pressure is high, the smell will be also high. Okay, so here in this beaker there is 40% alcohol, and next I'm going to add sodium chloride, a small amount of sodium chloride to this beaker. Okay, so what happens now, because this is a solution, I am adding as a solvent, we are adding sodium chloride, a solute. Okay, so at that time what will happen? So suppose you are adding sodium chloride, there will be a reduction in the smell of 40% alcohol. But you see that there is 40% alcohol always. There is only change in the reduction of the vapor pressure, that means reduction in the smell. So you see there is an important effect here we can observe. That means the amount of alcohol is similar before adding NaCl and after adding NaCl, but we feel that the concentration of alcohol is decreased after adding NaCl. So you see, this is our feeling. That means we feel that when you are after adding NaCl, the concentration of alcohol decreased. That is a very important concept in electrochemistry, because the electrochemists are dealing with these type of solutions. Okay, so once again I am telling you, before adding NaCl and after adding NaCl, we feel that there is a change in concentration of alcohol, but there is no change in alcohol. We know that the beaker contains 40% of alcohol. That means there are two types of concentrations. When you are talking about the concentrations, there are two types of concentrations. One is called the real concentration, and other one is called the perceived concentration. So real concentration means what? Real concentration means before adding NaCl. After adding NaCl, the concentration of alcohol, we feel that it is decreased. That means it is known as the perceived concentration. Okay, so we are now entering in a field of perceived concentration. That's a very important concept. I can tell you another example related to the perceived concentration. You can feel that in a gravy, the gravy has a particular smell because of the spices you added in it. Suppose you add the sodium chloride, table salt in it, the reduction of the smell is observed. That is another example of this perceived concentration. One more example I can tell you, that is you know that you are all using perfumes. Okay, suppose this is your perfume bottle, you are all using good perfumes. Suppose it is a cologne perfume. Normally it consists of 80% water. The perfume consists of 80% water and around 12% alcohol. So 80% water and 12% alcohol, and the rest percentage is some esters. You know that esters are adding in perfumes for giving the color and smell. So you see 80% water, 12% alcohol, and the rest is only the smelling component. Okay, so this alcohol percentage is very important. What alcohol is doing? Alcohol will make a feel that the ester concentration is very high in this perfume. The actual concentration is always similar. Okay, suppose you are adding ester in 80% or ester simply in water, you will not feel the ester concentration is very high. But when you add alcohol, you feel that the concentration of ester is very high. That is one of the important technique in perfume industry. That means if you are adding a little bit alcohol, there is a feeling that the concentration of the ester in it is very high. That is also known as the perceived concentration. So that means perceived concentration is the concentration we feel. Okay, we feel when you are feeling this. Suppose you take this example, 40% alcohol is there in this system. Before adding NaCl, there will be a particular pungent smell, and when you are adding NaCl, you feel that the smell is reduced. That particular concentration we are feeling is known as the perceived concentration. So there are two types of concentration: real concentration and perceived concentration. Okay, now we can play with the perceived concentration. So we have to find out the quantitatively the perceived concentration. That is also very important when you are dealing with electrochemistry, because electrochemists are dealing with the solutions, different type of electrolyte solutions, where we need the term called activity. Okay, so we can take the quantitative determination of this activity. Okay, so you can represent the perceived concentration as A. Okay, A is actually known as the activity, and this A is actually equal to this C. You know what is C? C is the real concentration by C0 into a term called gamma, that is the activity coefficient. Okay, so what are the things you can discuss? A is the activity, that means the perceived concentration. So perceived concentration you can also call A, that is the activity. A is equal to C by C0. What is C? C is the real concentration. I told you. Okay, it is suppose it is in mole. It is mole dm raised to -3. That is the unit. What is the unit? So what do you mean by this C0? That's very important, because we need these terms activity and activity coefficient term dimensionless. It's a dimensionless quantity, A and gamma. So in order to make it dimensionless, what we can do? Here you have a C0. I told you that this C0 is nothing but 1 mole dm raised to -3. Okay, so what will happen? You see, there is a particular dimension is here, and here also the same dimension. and it's 1 mole dm minus 3. So automatically it will cancel. So it will make this A and gamma dimensionless. Okay. So what is this gamma? I told you gamma is known as the activity coefficient. So this is the another term I told you, activity coefficient, that is the gamma. So gamma means what? Here gamma, you can write gamma is equal to what? Gamma is equal to A by C into C0. Okay. So C0 you need not consider, because C0 is 1 mole dm raised to minus 3, and simply you can write this gamma is equal to A by C. So what is gamma? Gamma, I told you that activity coefficient. So activity coefficient is the ratio of perceived concentration to the real concentration. Okay. So you see this equation, it's a very important equation. It's a dimensionless quantity. Gamma is equal to A is the perceived concentration divided by C. C is the real concentration. Okay. So you see this equation, we have started it from one or two examples. One is the example of the addition of sodium chloride in 40% alcohol solution. That means there is a concentration difference we are feeling, that is known as the perceived concentration. So here also, if you are adding 12% alcohol in this system, you can feel that the ester concentration is increased, that is also known as the perceived concentration. Okay. Suppose you are taking a very dilute solution. So I will go to some thermodynamic concepts related to this one. So I am going to some real concepts related to the activity, some reality. That means suppose you are taking a solution, at what range you can expect this concentration change, not range, concentration change. So there will be a range of dilution. You can feel the activity. That is why I told you that if you are taking a very dilute solution, what will happen? In the case of very dilute solution, that means concentration is in the range of 10 raised to minus 4 mole dm raised to minus 3. It's a very dilute solution. In the case of very dilute solution, this activity, this perceived concentration is equal to the real concentration. That means in this range, this difference it is not effective. That means in the case of very dilute solution, A is equal to, that is the perceived concentration is equal to the real concentration. Okay. But you see, we are always dealing with the solutions which whose concentration, the concentration is above this 10 raised to minus 4 mole dm raised to minus 3. That is why we need the activity, the term activity. So normally in the case of, that means electrochemistry, we are dealing with somewhat concentrated solution. So in the case of concentrated solution, that means it's a concentrated solution. So in the case of a concentrated solution, this term activity will come. That means it is above 10 raised to minus 4 mole dm raised to minus 3. So now the term activity is coming. So when the concentration increases, this activity will be smaller than the real concentration. That means the perceived concentration is lower than the concentration. Then what happens to this gamma? Gamma is equal to A by C. So when concentration increases, this will be low, activity will be low, and this will be high. This real concentration will be high. That means gamma will be smaller than 1. Gamma will be smaller than 1. So this you can express in terms of a graph. Okay, if you are plotting gamma, so in your x axis, in your y axis gamma, and your x axis concentration. The x axis concentration, what will happen? Here gamma, and here it is concentration. So here you see, when the concentration increases, your gamma, the variation will be like this. Okay, that means when the very low concentration, there is gamma will become unity. Okay, unity. That means A is equal to C. So very low concentration, what happens? A is equal to C. A is equal to C. When the concentration increases, what happens? The gamma, the activity coefficient will gradually decreases. Okay, so this is very important concept. This is also you can also call it as thermodynamic activity. Then I will give you some information about different type of systems. What is the activity value in different type of systems? We can see. First, we can take the solid. Okay, solid. Suppose you take a solid. What will be the activity? What will be the activity? So in the case of solid, and you can add it as pure solid. Suppose there is a pure solid, that means zinc or copper or some metal or something. In the case of a pure solid, its activity is equal to unity. Activity can be considered as unity. Suppose you are taking an alloy. That means your tin means 30%, tin 30%, and copper 70%. Your activity of tin is equal to 0.3. Activity is 0.3, and activity of copper is equal to 0.7. It's a dimensionless quantity. Okay, 0.3 and 0.7. So it is also called the mole fraction. So when you are taking the alloys, the activity is related to equal to the mole fraction of the system, mole fraction of one component in the system. So that is the case of when you are considering pure solid. When you are considering the gas also the same. You can see when you are considering the gas, normally what we will take for the, instead of the concentration term, we will take the term pressure P. So your gamma is equal to P by P0. So here also, in the case of a pure gas, you can take it as the pressure as unity, and when you mix together, when you make gas mix, you can also go for the mole fraction, same as the other. So what is in the case of the solution? That is our interest, because the electrochemists are mainly dealing with the solution. So electrochemists are normally will not deal with the mixture of solutions. So that is rarely the electrochemists are dealing the mixture of solutions. But electrochemists will deal with not the mixture of solution, mixture of solvents, that type of things. Okay, the electrochemists are mainly dealing with the solution. That means the solute plus solvent. That is the electrolytes. Okay, solute plus solvent. So here what will happen? Here if you are going for gamma. That means here you see most of the time we are dealing with the concentration above 10 raised to minus 4 mole dm raised to minus 3. So, we are not considering very dilute solution in the case of electrochemistry. So, there the term activity is very important. So, activity coefficient is also important. We have to find out the activity coefficient. So, for that we need the help of a law called Debye-Huckel limiting law. So, in the next class I will explain what is Debye-Huckel limiting law. So, today we will discuss about we are discussing about activity and activity coefficient. Okay. So, next I will tell you more about some terms which is very much related to the Debye-Huckel theory. That will be helpful when I am explaining Debye-Huckel theory in the helpful for you to explain Debye-Huckel theory very correctly. Okay. So, I will just give you some different types of terms which is very much useful for the for explaining Debye-Huckel theory. Okay. So, this is our concept of activity and activity coefficient. Again I am going to explain something related to activity coefficient. We can take an example of a salt. So, normally you know that in an electrolyte there are two types of ions, anions and cations. You see anions and cations, cation, because it's suppose it is a KCl solution. You can see there is K plus and Cl minus. So, you can also write like this: activity coefficient of K plus and activity coefficient of Cl minus. But you see there is an important concept is coming here. It is impossible to find out the activity coefficient of the individual ions. Normally you will get it together. So, it is not possible to find out the activity coefficient of K plus only and activity coefficient of Cl minus only. So, we need a very important another term. It is known as the mean activity coefficient. So, normally we will not work with simply activity coefficient. That is not possible because we are considering an electrolyte consists of this type of anions and cations. So, together only you can find out the activity coefficient, that is known as the mean activity coefficient. So, it is geometrically it's a geometric mean. You can find out mathematically you can find out the activity coefficient like this. Suppose you are considering I told you that we are considering KCl is a 1:1 system. You see the activity coefficient can be expressed for the KCl. Activity coefficient can be expressed activity coefficient can be expressed like this: gamma plus minus, that is the mean activity coefficient. The mean activity coefficient you can represent like this. It is a root of activity coefficient of plus ion into activity coefficient of the minus ion. That is why I told you that is a geometric mean. Alpha gamma plus or minus is equal to, for this particular 1:1 system. Suppose you are considering it for another system. suppose K2SO4. Suppose you take K2SO4. K2SO4 is a 2:1 system. 2:1 system. So how you will write the gamma plus minus, that is a mean activity coefficient. Mean activity coefficient. So you see here the ions. How many ions are there? Here only 2 ions, K plus and Cl minus. Only 2 ions. That is why gamma plus into gamma minus. So here how many ions are there? K2 means 2K plus and SO4 minus. That is 3 ions. So you cannot take a square root. You can take the cube root of gamma plus means gamma plus is 2. That means gamma plus square into gamma minus. So like that you can express the mean activity coefficient. You can try it for another compound Mg3PO4 PO4 twice. You can try how can you write this gamma plus minus. Okay, so I will explain another term before I am stopping the class. That term is also very important when you are dealing with the Debye-Huckel theory. It's also just like a concentration term called ionic strength. Because you see in electrolyte we are dealing with ions, anions and cations. So the number of ions in a system is very important here. In an electrolyte system, the number of ions is a very important quantity, and not only number of ions, its charge also very important. So we need a term connecting. We need a term which is effectively connecting all these things. That means the number of ions and charge of the ion. So that important term is known as the ionic strength. So how can you express the ionic strength? Ionic strength can be represented by I, that is equal to half into sigma. I is equal to 1 and I is equal to I. I is the ion. I is the ion we are dealing with, and you see I is equal to 1 and I is equal to I, and our Ci Zi square. So this is the equation for ionic strength. What is this C? C is the concentration of the ion, and Z is the charge of the ion. Okay, so I is the ion. So this is the equation for ionic strength. So I told you ionic strength is a very important quantity when you are dealing with the Debye-Huckel theory. So we are going to discuss about this ionic strength. Okay, I will give you some idea about ionic strength. Taking a solvent, that is the 0.01 molar NaCl. 0.01 molar NaCl. So NaCl, you know, that is a 1:1 system. 0.01 molar NaCl. So how can you write the ionic strength? I'll write here. Okay, that is I. Here I is equal to what? I is equal to half into what? We'll take the first ion, that is the Na plus. That means you can also take the concentration of Na plus into its charge. That means the plus 1 square. Okay, plus there is a sum. You see, this is a sum, and you can take the another ion Cl minus, concentration of Cl minus into -1 all square. So that is the ionic strength. And I told you that this is a 1:1 system. Here in this type of a system, the concentration of Na plus is equal to concentration of Cl minus, that is similar to the concentration of NaCl. You know that NaCl. So instead of writing Na plus and Cl minus, you can also write NaCl. So how can you write like this? This ionic strength I is equal to half into concentration of NaCl into 1 plus concentration of NaCl into 1, right, into 1. So what is this concentration of NaCl? That is 0.01. This is 0.01 and this is also 0.01 molar. So what you will get finally you will be getting 0.01 molar. Okay. So this is actually method to find out the ionic strength. So I will give you one more example. That means the magnesium chloride. We can also just find out the ionic strength of 0.1 molar solution of magnesium. Okay. 0.1 molar magnesium. So I am just writing another example, that is the 0.1 molar MgCl2. 0.1 molar MgCl2. So how can you write this one? I told you that here you have Mg, the concentration of this Mg part. Okay, Mg is you can write this MgCl2. What about the Cl2? What about the Cl2? Sorry, what about Cl minus? Cl minus is equal to what? There are two Cl minus. Okay, there are two Cl minus. That means 2 into MgCl2. 2 into MgCl2. There are two 2 Cl minus. So how can you write the ionic strength I is equal to half into how much it is? 0.1. Okay, 0.1 into its charge. So what is the charge? This is 2 Cl. This is what is the charge? 2 plus Mg 2 plus. So it is plus 2 all square, plus 2 all square plus what? Point again, what? Again point, not 0.1, again you should write 0.2. So this is 2 into MgCl2 into minus 1 square, that is half into 0.1 into 4 plus 0.2 into 1, you will be getting 0.3 m. So this is the actually ionic strength of this particular solution. Okay, so you please please refresh once again. I already told you many terms today. One is the activity and activity coefficient, and another important term is the mean activity coefficient and ionic strength. So all these things we need in electrochemistry, because the electrochemists are dealing with electrolyte solutions. So there the concentration term, for explaining the concentration we need a term called activity, and also all these parameter, all these activity coefficient, mean activity coefficient, ionic strength, all these things we need for the explanation of Debye-Huckel theory. Okay. So the next class I will tell you about the origin of Debye-Huckel theory and the explanation and application of the Debye-Huckel theory. Thank you.